Afternoon. This is a review for all of those who are not here today. Please make sure you do this before you take the test on Thursday. I'm going to go over this sheet is going to be in notes. I'm going to send you a copy of this. If you just want to review these notes, that's fine. You obviously won't have a copy of this paper, but hopefully it'll still give you a better idea what's on the test. So today was do now that I'm going to do with your classmates is cold water is poured into a hot coffee pot. Which direction would heat flows? Well, the answer to this question is that heat flows from the hot pot to the cold water because heat only flows in that direction. Number two, when will the heat flow fastest? As soon as the water is poured into the pot or after they begin to reach the same temperatures. The answer to this is as soon as the water touches the pot or is poured in the pot, because at that point their difference in temperature is greatest, and that's going to have the highest rate of heat flow. The objectives for today is making sure that everybody feels really comfortable knowing what's on the test and that everyone feels prepared for the test. So I'm going to go through the notes that I'll go through in class with everyone else. If you were able to download and print the document, you could just fill in the blanks. Otherwise, just make sure that you know this stuff. So the first item on the I CAN checklist is that I can define temperature, heat, thermal energy, and thermal equilibrium. So let's go through those. We know temperature is a measurement of how hot or cold something is. It is directly proportional to the average kinetic energy of a substance's molecules. So those little guys are moving back and forth. As the temperature increases, they are moving faster. The higher the temperature, the faster the motion of the molecules. There are three major scales that people use to measure temperature. The first one is Celsius. Scientists created it based on water. So at 0 Celsius, when water freezes, 100 degrees Celsius is when water boils. And this is the metric unit for temperature. Kelvin is a degree that's the same size as Celsius, but we call 0 Kelvin is at absolute zero when molecules have no thermal energy and are not moving. Again, 0 degrees Kelvin has never been witnessed in science. This is just what we can imagine would happen. Fahrenheit, again, we are the only major country to use, the major economy that uses Fahrenheit. Water freezes at 32 Fahrenheit and it boils at 212 Fahrenheit. Heat, we know, is energy that transfers from one object to another because of a temperature difference. Matter doesn't have heat. It does not contain heat. It has internal energy or thermal energy. Heat is energy moving from one area to another. It moves from high to low temperature. You also might see that it's called energy in motion. And I underline in because we know that kinetic is energy of motion. Thermal equilibrium is when objects reach the same temperature. Heat's going to flow between the two substances until they reach thermal equilibrium. So what happens with the thermometer is that it really shows its own temperature, which is why you don't take your temperature as soon as you pop the thermometer in your mouth. You let that thermometer get to thermal equilibrium with your mouth. If we put a cold rock into warm water, it'll cool down the water and the water will warm up the rock. Internal energy is another name for the total energy inside a system. It includes the thermal energy and potential chemical energy, but for the most part, we're only focusing on this thermal energy part. It's going to change when heat flows. If something takes in heat, it goes into an object, the internal energy increases. If an object is releasing heat, its internal energy decreases. Temperature is not necessarily going to change. For the most part, it does, but when objects change state of matter, so if ice melts, or water freezes, or water boils, or it condenses, it's going to take in or release heat, but during those phase changes, its temperature doesn't actually change. So just that is not on the test. This section right here, the temperature does not necessarily change, but that's just something you should know. Apologies for how big this is. Now, how we measure heat, it's measuring, we use it like we did in our lab. We measure the temperature change of a known mass of a substance that absorbs the heat, like the water in our lab. Calorie, excuse me, is going to be the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And kilocalories are what we use in our food, and that's 1,000 scientific calories. Heat is required to raise 1 kilogram of water by 1 calorie, that's a kilocalorie, and we call it calorie with a capital C as opposed to lowercase calorie. For some reason, I have 2 thermal equilibrium problems, but our slides, we're going to flip over here to this. So what I gave to people today in class is I went through the ICANN checklist and put either the notes, which I just went through, under the first one that says define temperature, heat, thermal energy, and thermal equilibrium. And then I gave some practice problems. So at this point, I'm going to ask you to try these problems. If you were unable to download the worksheet, please at least just write down the answers on a separate piece of paper, and then I'm going to show you the answers. So again, at this point, you need to pause the video. Once you're done, here are the answers. A beaker of water with a temperature of 10 degrees Celsius is placed in a beaker of equal amount of water with a temperature of 80 degrees. What will happen to the temperature of the water which started at 10 degrees? It will increase. That heat is going to flow from the hot water to the cold water. What will the final water temperature be? Well, we got to figure out what's the difference. So we take 80 minus 10 and we get 70. Well, 70 divided by 2, because it's going to be in the middle, is 35. So the final temperature is 35 less than 80, 35 more than 10. So the final temperature is 45 degrees Celsius, halfway in between. And again, we can only know the exact temperature, final temperature, if given an equal amount. Number 3, I can predict a relative final temperature of 2 unequal amounts of water when given their starting temperature. So if there was twice as much hot water than there was cooler water, how would the final temperature compare to 2 starting temperatures? Well, if there was more hot water, it would be closer to 80 degrees than 10 degrees. If I asked it a different way, you could also write more than 45 degrees C. Excuse me. I'll probably just do one question like that. The next bullet point, a lot of people ask questions about, so I thought I'd put 2 examples, even though there's only one on the final test. You put 100 milliliters of water in a can above a flame. This is my flame. The temperature rises by 2 degrees Celsius. If you add the same quantity of heat to 200 milliliters of water, by how much will the temperature rise? Well, now we have more water, and it's 200 milliliters. Well, I see this is twice as much water. I'm putting the same amount of heat in it, so it's going to rise. This is going to be an inversely proportional relationship. So volume and temperature change. And so if this is multiplied by 2, then we have to divide, this was multiplied by 2, so we have to divide this by 2. So the answer is an increase of 1 degree Celsius. Now repeat that. This was multiplied by 2. This was multiplied by 2, so we have to divide the temperature change by 2. And so we have 201. You put 1 liter of water on the stove for 10 minutes. The temperature rises by 5 degrees Celsius. If you put a half of liter of water on the same stove for 10 minutes, how much will the temperature rise? Well, to go from 1 to a half, we divided by 2. So instead of dividing, we need to multiply by 2. So we need to multiply 5 by 2, which gives us 10 degrees Celsius. So whatever you do to one, you do the opposite to the other. Number 6, underneath the bullet point, I can explain the direction that heat flows and how the rate is affected by temperature difference. You accidentally locked yourself out of your house on a cold day. Your feet get very cold while you're waiting for your sister to get home and let you in. Warm up your feet. You fill the bathtub with hot water and put your feet in. Which way does the heat flow? Heat flows from warm water, or hot water, excuse me, to cold feet. When does the heat flow fastest? When you put them into the hot water, or later when your feet are almost the same temperature? When you put them in the hot water, because heat flows faster when the temperature difference is greater. Excuse me. I can explain that heat is the flow of thermal energy and that objects do not contain heat. Your little sister tells you that her hand has heat. You need to correct her. You should say, no, your hand has thermal energy. If you really want to get into the nitty-gritty details, you could tell her that her hand releases heat when she touches something cold. I'm not going to do anything, but it's for number 9 and 10, but you need to know what you wrote for your CER. This bullet point, I can use data to explain which organic molecule stores the most or least chemical energy. I'm not going to grade it like a CER, but you're going to have to write a paragraph explaining, using the data and explaining this. And the last one, I can graph the change of 2 temperatures. This is basically doing the graph from the thermal equilibrium mini lab. I'm also going to send you a Kahoot that we're going to hopefully get to in class. So I hope this helps. Please let me know if you have any questions. I will be available before school on Thursday. Hope your day of protest went well. You are in our thoughts and prayers.